So in allosteric modulation, we know that allosteric means that our compound is going to bind to a different site than the agonist. And when it does that, the only way that it can exert any effect on agonist binding is if it causes a conformational change in the protein. This is not it just simply gets in the way of the agonist. This is going to have some sort of effect on the protein, causing it to change shape, which changes the agonist binding site and changes the affinity of the agonist for the protein. So in this figure, we see a protein, and we have two binding sites. The agonist binding site, the ICAM1 binding site, is up at the top of the protein, but the allosteric site is down below. And so if we add an allosteric modulator here, it's going to bind at the bottom of the protein, cause a large conformational change in the protein, which is going to change the shape of the pocket up at the top of the protein and change the binding of the agonist. One big advantage, among others, we'll see other advantages, is that allosteric antagonists tend to have fewer side effects than orthosteric antagonists. Remember that orthosteric antagonists bind to the agonist binding site. And our body only has so many agonists, right? And think of histamine. We have one histamine molecule, but we have multiple histamine receptors. If we create an orthosteric antagonist that binds to the histamine binding site, most likely that orthosteric antagonist is going to be an antagonist for all of the histamine receptors. However, if we bind someplace other than the agonist binding site, we have more choice in where we bind. And if we have a choice, we can pick a part of the protein that is unique to that particular receptor. We can find a part of the histamine 1 receptor that is different than the histamine 2 receptor. In that situation, we can be more specific in which receptors we inhibit. And by doing that, we reduce off-target effects. Maybe inhibiting the entire class of receptor is not what we want to do. We only want to inhibit one of them. Another example of how an allosteric molecule can reduce side effects is that it is only going to potentiate a response. So in this situation, we are going to be increasing the binding of our agonist. And so in this situation, the allosteric molecule binds and increases the agonist binding in a different location. So because we are binding in a different location, we are not going to have any effect. We are not going to cause any response at all when we bind. But when the agonist binds, we get the effect. So imagine a situation like Alzheimer's disease. And I'm looking at that and I'm realizing I'm missing the H in Alzheimer's. Alzheimer's disease is very, very simply a decrease in neuron signaling, okay? And a lot of times, the agonist is present. What is not working is the receptor on the neuron. And so essentially what we do is we increase the ability of the neuron to respond to the agonist. Now, if we add the allosteric drug, it is going to bind to all of the receptors in the body. However, it's only going to have an effect where the body created the agonist. And the body created the agonist in that location because it wanted a response or an effect in that location. So all we are allowing to do here is to allow the body to do what it was trying to do anyways. And we are not going to create an effect where the effect does not belong. So like we mentioned, the allosteric molecule is going to cause a change in the conformation of the protein. Receptors are constantly changing shape. Not only do they change shape between the active and inactive conformation, but there may be different conformations somewhere in between. Maybe there's multiple inactive conformations that are very similar to each other. The allosteric modulator is going to have prefer to bind to one of these conformations. And when it does bind to the conformation that it prefers, it's going to lock that protein into that conformation. So imagine a situation where we have a receptor that can be in conformation A or conformation B. But it spends 99.9% of the time in conformation A and only 0.1% of the time in conformation B. If we come up with a molecule that prefers to bind an allosteric drug that binds to conformation B, every time a receptor switches from A to B, it's going to be stuck in B. And over time, the receptors are going to shift from mostly in conformation A to mostly in conformation B. It's going to act like a doorstop and prevent it from switching back to conformation A. Another advantage or disadvantage, depending on the situation, of an allosteric modulator is that it is going to provide incomplete inhibition. Remember that all it's going to do is it's going to change the affinity of the agonist to the receptor, and it cannot prevent the agonist from binding. And so no matter how much allosteric inhibitor you bind, you are always going to have some agonist binding. Now, if you want to absolutely prevent agonist binding, this is not good, because you're still going to achieve some response. You're never going to get down to 0% response. But imagine a situation where you don't want 100% inhibition. Maybe 100% inhibition is going to be toxic. You want 50% inhibition. If you are going to achieve 50% inhibition with an orthosteric antagonist, your margin for error is going to be very small. Not enough drug, you're not going to get enough inhibition. Too much drug, you're going to get too much inhibition and get toxic side effects. But if you can make an allosteric modulator that maxes out at 100 or 50% inhibition, you can give very large doses of drug. And so you can start off with a very high concentration of drug, then as it gets metabolized, you still have enough in the system to achieve 50% inhibition. Whereas with the orthosteric antagonist, the amount of inhibition changes as the drug gets metabolized. And so you get a response curve like this over time. But with an allosteric modulator, you can keep it completely flat as long as you maintain a high enough concentration that you have full inhibition, which in this case is only 50%. Now, we've already seen that the modulator can have increasing or decreasing effects on the agonist binding. And it can affect both the affinity and the efficacy separately. It can increase one, decrease the other, decrease one, increase the other. They're completely separate. So we, on the left, are looking at this. So in this situation, we have a receptor and an agonist is binding. When it binds, it has an effect. In this situation, we are going to refer to affinity as alpha. Now remember, a few lectures ago, we had alpha being intrinsic efficacy. In this situation, it is affinity, and efficacy is beta. Think of alpha comes before beta, right? A before B. You have to have affinity, you have to bind before you get efficacy. That's the way I keep track of which one is which. And so if we add an allosteric modulator, we can change alpha, we can change beta, or we can change both, and they can go in either direction. And so we have lots of different combinations. Here, we are looking at the effect of modulators on dose response curves. And so if we start with changing alpha only and not changing beta, and so that is the top left and the middle left and middle right here. And so in this situation, all we're doing is changing affinity of the agonist. That's changing the potency. We expect a shift left or right of our dose response curve for our agonist. If we increase affinity, we're going to shift to the left. If we decrease affinity, we're going to shift to the right. Now, if we look at where we do not change affinity, but only change efficacy, we are going to see primarily changes up and down in the curve. Increasing efficacy causes it to go up, decreasing efficacy causes it to go down. You may see some changes in left and right, but they are not really all that important in this situation. Remember that changes in efficacy cause the dose response curve to go up or down. And then you can get combinations of changes in alpha and beta. You can go up and left, you can go up and right, you can go down and left, or down and right. One way that we can use allosteric modulators is as a co-therapy. So in this situation, we are looking at the binding of an antibody called 45531 to the CCR5 receptor. And this is a treatment for HIV, or to prevent HIV infection. HIV virus particles will bind to the CCR5 receptor and get taken into the cell. And so if the antibody is already bound to the receptor, HIV cannot. And so what we can do is we can add an allosteric modulator that is going to control the binding or increase the binding of this antibody to the receptor. So on this graph, x-axis is increasing amounts of antibody, and on the y-axis it says counts, but that is how much antibody is bound. This is just a binding curve. In the absence of any sort of allosteric modulator, we get the black line. So that is the one the furthest to the right marked solvent. And so as we add enough antibody, eventually we get some binding. For some complicated reasons we don't need to worry about. If you add too much antibody, the antibody binding actually goes down. Now, if we add an allosteric modulator, this SCHC or the aplaviroc, notice that the antibody starts binding at a much lower concentration. And so we can add less antibody. Antibody drugs are very, very expensive, and so the less we can use, the better. So as we've seen, we have multiple effects that an allosteric modulator can have on a receptor. It can increase or decrease beta, increase or decrease alpha. So we're going to use those effects to define different types of allosteric modulators. A negative allosteric modulator, a NAM, is going to have an alpha and or a beta less than 1. If it decreases one of them, it is a negative allosteric modulator. We see that in the graph on the top right. So the dark line is a dose response curve of the agonist in the absence of allosteric modulator. The curve that I'm tracing here, the one that starts further right and ends at the same location, still reaches one response, is going to be decreasing affinity only. The one below that is going to be, looks like decreasing alpha and beta. We shifted to the right and down. Something unique here is we can have what's called a NAM agonist. This is a negative allosteric modulator that through one mechanism or another actually does produce some response as its own. It's a partial agonist that binds to an allosteric location and decreases either the affinity or the efficacy of our traditional agonist. So in this situation, we see that both NAM agonists start the response higher. However, one of them, when we add the agonist, gets up to 100% response, while the other one does not. But both of them change the potency of the agonist. Conversely, we have positive allosteric modulators. A PAM has an alpha and or beta greater than 1. That's the top curve here. We shift the dose response curve either up, increasing efficacy, or we shift it to the left, increasing potency or affinity. A PAM agonist is what you think it is. We're going to increase agonist affinity or efficacy while having some partial agonist activity of itself. We can also have a combination of positive and negative effects that would be a PAM antagonist. In this situation, we have an alpha greater than 1 and a beta less than 1. Studying allosteric modulators is a complicated situation because unless it is a PAM agonist, the allosteric modulator binding to a receptor has no inherent effect, right? All it does is it changes the binding of the agonist. And so if there's no agonist present, there is nothing that's going to happen when an allosteric modulator binds. And so an allosteric modulator, its effects are only measured as effects on agonist binding. And so the IC50 of an allosteric modulator is dependent on how much agonist is present. Not only how much agonist is present, but what the agonist is, because an allosteric modulator may have a different effect on the binding of one agonist versus another agonist that binds to the same agonist binding site. And so what you need to take from this is that when you read or report an IC50 for an allosteric modulator, it is very, very, very specific. It is only going to be valid in the same exact situation. If you change the system at all, the IC50 is going to change. I hope that made sense to you. If it didn't, you can always let me know.